I decided to make a video instead of taking pictures because it'd be easier to explain, I believe. So here we've got three-phase secondaries on the transformers. I didn't show any of the primaries because it's not really needed. Anytime you have an even voltage, like here on this Y, your Y is always, your neutral comes out of the center tap, and it's grounded. So you have your 280 or 208 volts from phase to phase, but you have 120 volts from phase to neutral or phase to ground. Same thing on the 480. You'll have 480 volts phase to phase, and 277 volts from phase to neutral or ground, because your neutral is grounded. There's actually a bond inside of those pad mount transformers. So here, if you have a delta secondary, you'll have 480 between the phases. If it's a 480 secondary, or 240 between the phases if it's a 240 secondary, or 230 as you noted, same difference. But there is nothing that is bonded to ground on that secondary, and that's normal. I think we're getting away from these a little bit and going with the Y configuration on the secondary so that you can use your 277 volt lighting and then have your on your 240 would actually be 208, and you'd be able to utilize 120 on that. It just gives you a more variety of electrical systems that you can use. Now here's the one we're discussing. I was calling the wild leg. In this case, it's B phase. It's a delta. It's 240 volt secondary. So between each of the phases, you have 240 volts phase to phase. But in this case, they put a tap between A phase and C phase, and they ground it, and that also becomes your neutral. So now you have 240 from phase to phase. But since you've taken your A phase to C phase, 240 volts, and you split it in half, you now have 120 volts from A phase to ground or neutral, and you have 124 or 120 volts from C phase to neutral or ground. Now, if we take a look, this is where the wild leg comes in. If you take a look, we have a full winding and a half at this point between B phase and your neutral. You're not going to get 120 volts out of that. It's somewhere around the neighborhood of 190 volts, 197. You don't see too much of this anymore because people would put their 120 volt outlets on B phase, and then when you'd plug your drill into it, your drill would blow up because your voltage is 190 instead of 120. But that's where, and I should have written it down, but your B phase in this case would be the wild leg. Now that we're talking secondaries on transformers, I have, in my many years of experience, run across one case, and this was in Florida, one case of what they call a corner grounded delta. And what they did on the corner grounded delta is exactly what it sounds like. They grounded the corner. So if you're in your disconnect and you're measuring your voltage, you'll have, in this case, 480 volts from A to B, B to C, C to A. You got 480 volts. But if you start checking the ground, A phase to ground, you have 480. B phase to ground, you have 480. C phase to ground, you have 0 volts, because that's the phase that's grounded, or that is tapped to ground. I tested this theory as a young kid. I took like a quarter amp fuse and put between C phase and ground, turned the disconnect on, fuse did not blow. So it is truly a corner grounded delta. And same thing on the 230 volts we had. It was also a corner grounded delta. 230 phase to phase, 230 from A to ground, 230 from B to ground, but C to ground was 0 volts because that's the one that's tapped to ground. It was very unsafe. I worked behind a colorblind electrician. Couldn't tell the difference between white and green, and we used SO cord for our electric motors in this factory. So him not knowing which was which always put either the white or the green on C phase. And sometimes the conduit ended up being your carrying conductor in this case. But anyway, that's basically the secondaries of your transformers. I hope this makes sense. I did my best on this. You can look all these up. Google. I just figured for me it was easier to draw it out. I hope this helps. Any questions, feel free to ask.